So, hi everyone. I'd like to start by thanking Lev and Guy and all the support team for making this happen. It has so far been, well, it has been a great meeting. It was definitely a success. And thank you, Lev, for the invitation. I'm very happy and pleased to be here. So, 2 weeks ago, there's this, I get rid of that. There you go. So 2 weeks ago, there was an article published in the Scientific American titled, "The Universe is Not Locally Real, and the Physics Nobel Prize Winners Proved It." Now I could dedicate my talk to taking issue with the fact that we don't prove such claims in science, or to the fact that the universe is real, but I assume that I don't really need to convince you of anything. Instead, I'll be really speaking about the question of locality, which creates enormous confusion in quantum theory. So my claim is quite simple. Quantum systems can be described completely and locally, and we should do so. So let me elaborate on what I mean by completely and locally. We're all aware that if Alice and Bob share an entangled pair of particles in a Bell state, they have a local mode of description, and this is well known from the reduced density matrices. And it's local in what sense? In the strongest possible sense. In Einstein, according to Einstein criterion of locality, namely that the description of system A is independent of what is done with system B, which is spatially separated from the former. So that means that whatever Bob does to his quantum system may affect his own reduced density matrix, that's fine, but it's going to leave invariant Alice's reduced density matrix. However, it's not complete, and what I take as a criterion of completeness is that we cannot compute the distributions of all joint measurements from the description of Alice and the description of Bob. As you well know, though the object that encompasses all joint measurement is the global state vector, or the global, or its associated density operator. And we all know that from rho A and rho B, we've traced out too much information. We can no longer recombine them and hopefully predict everything out of possible interactions. Yeah. However, we also know that there's a global state vector as a mode of description. So that means that Alice takes as her mode of description the whole state vector, and so does Bob. Then we have a complete description, because trivially from Alice's description, phi plus, and Bob's description, phi plus, we can recompute phi plus. But it's no longer local, according to Einstein's criterion. Why? Because if Bob affects his qubit, or his quantum system locally, it's going to change his own description, which is fine. But it also happens to change Alice's description when we take this mode of description, which seems to create confusion about the question of locality of the global state vector. So we seem to be stuck in a dichotomy, and when we think about this problem, we sort of, oh yeah, well, there's this dichotomy of quantum theory. We describe entangled quantum systems either as local or as complete, and we have to choose depending on the problem that we're interested in solving. However, this dichotomy has been proven false more than 20 years ago by Deutsch and Hayden. So to be clear, they exhibited a mode of description. It's called a descriptor. Alice has a descriptor QA to describe her quantum system, and Bob has descriptor QB to describe his quantum system. And it's entirely local, so whatever Bob does to his qubit, he applies a unitary, he measures it, he throws it in a black hole, whatever he does, it's going to affect his descriptor, take QB to QB prime, but it's going to leave invariant QA. And it is complete in the sense that if one is given QA and QB as mathematical objects, they can recover the whole wave function. More recently in the literature, there has been two other proposals for what I call quantum locality. They're the proposals of Raymond Robichaud. One of them, this one here, it's called evolution matrices, and it works within the quantum formalism. While the other one is a more general approach. It actually holds for all for a family of theories on which operations form a group and so on. But quantum theory is instantiated, is one possible theories. And so when we look at quantum noumenal states, you can also look at this diagram, which really shows well the structure. So there are some noumenal states, NB and NA, which admits a product structure which has no counterpart at the density matrix level. So that's one way to think about those local descriptions. And yeah, so in the quantum case, in fact, I showed them to be, the three of them, all formally equivalent in this paper published last year. In this paper also I investigate the consequences that it has on how we have to think of then the objects to describe quantum theory and the consequences for the universe as a whole. Now, we've been proposed with many formalism, alternative formalisms to quantum theory, and so far it may look like I'm just proposing yet one more formalism to quantum theory, but that is not what it is. So Deutsch and Hayden paper hinges on Goethe's-Mann 1998, the Heisenberg picture of quantum computers, which is the Heisenberg picture of quantum computers. So it is the Heisenberg picture of quantum theory. It is the way in which theory has been discovered in 1925 with operators that evolve in time by Heisenberg here. So I want to stress that what I'm talking about is not about interpretations. It's about the mathematical formalism of quantum theory. It's take unitary quantum theory and see what it looks like in the Heisenberg picture. I could spend time to explain you how and why descriptors work and be on the roots of this tree, say. But I have done so in a paper titled The ABC of Deutsch-Hayden Descriptors. It's a paper that I have written and I had in mind somebody who has just done one course in quantum computation can read it and follow it. So please go see it if you're curious to know more about how it works. You can also look at my talk from last year's conference on the shoulders of Everett. It's available on YouTube. If I don't go in as much details, but I make comments about how it works. But what I want to be doing today instead is try to convince you of the explanatory power of descriptors. And to do so, then we'll tackle a problem, and it's the problem of teleportation, to find a way to explain teleportation. And so in what follows, in fact, I'm just being a voice of the Deutsch-Hayden explanation of teleportation in their paper in 2000. So let me go. This is teleportation with the 6 discoverers of teleportation. And I remind you the protocol. It starts with an entangled pair prepared. So a pair of quantum systems, a pair of quantum systems and in a Bell state, the phi plus state, which is going to be shared among Alice and Bob. And then Alice prepares a quantum state, a qubit, in the most generic qubit that she can make, alpha 0 plus beta 1. So think that Alice is actually putting her personal diary into alpha and beta. There's plenty of place in alpha and beta because alpha and beta are complex numbers, so they can encode a lot of information. And that's what Alice does. Now she performs a Bell measurement, which yields 2 classical bits of output. And she communicates those 2 classical bits to Bob over the phone. Bob then performs a correction. Depending on the 2 bits that he received, he will or not apply the Z gate, and he will apply or not the X gate. And at the end, we find that the quantum state in Bob's hands is alpha 0 and beta 1. This protocol is called teleportation, but my reading of this is that teleportation is the name of a problem. And the problem is, how do alpha and beta make their way from Alice to Bob? Reminding you that alpha and beta are a complex number. They contain, in principle, infinite amount of information, and only 2 classical bits have been communicated. So this is the circuit of quantum teleportation. You can see first this is the preparing the Bell state. This is the preparation of the psi by Alice. This is going to be the Bell measurement, the classical communication, and the error correction by Bob. Now, I represent the preparation by the unitary operator U, which maps ket 0 to ket psi, which enables me to start with qubits just in the state 0. Let's first do the computation. Remind you how the computation is done in the Schrödinger picture. We only need to investigate what happens at time t equals 3. At time t equals 3, the global state vector is written as psi tensor phi plus. That's what it is. And we can rewrite it. Now, psi, by definition, is this, alpha 0 plus beta 1. Phi plus, I disregard normalization, and phi plus looks like that, 0, 0 plus 1, 1. Now, I distribute it, and I'm going to look at the first 2 qubit registers. And having these identities in mind, where again, I disregard normalization, I can rewrite the first 2 qubits of each term as a combination of Bell states in this fashion. By reorganizing the term, we get this. And we already see some particularity here that alpha and beta seems to be already sitting on the 3rd qubit. But in some encoded way, and we know what is this encoding, it's in fact the Z gate and the X gate and the ZX gate acting on psi. So without even looking further, at time t equals 3, it seems like psi is already sitting on the 3rd qubit. And of course, we can, you can see what happens. After we do the Bell measurement, it's going to distinguish, say, the psi plus, and it's going to tell you to apply the correction X, and in all cases, we find psi at the end. But what I want to stress here is that even if we embrace completely unitary quantum theory, we're not making much progress. Because what we do here is we have those 2 extra qubits, which are going to record the measurement that are factored out. And after the Bell measurement, so at times t equals 6 here, well, they're going to get entangled with the quantum system, of the pair of quantum system in Alice's hands. And after the correction, psi is going to factor out. But unitary has not really helped us out to understand teleportation here. Yeah, psi is factored out and psi is teleported. The Schrödinger picture provides no satisfactory explanation. Let's do it in the Heisenberg picture instead. And I'm sort of in an awkward stance because I haven't told you how it works. But so it's a bit like if you have to explain quantum computation in 5 minutes to someone, and you're going to go, I don't have time to tell you the Hadamard matrix is. Don't ask me what's a ket, but the Hadamard does this. It takes 0 to 0 plus 1. So bear with me, right? And I'm not telling you about normalization, no time for that. Or you're going descriptors. So Heisenberg descriptors, you see that I've written them on each wire because I said they're completely local descriptions of quantum systems. I can write them down on the wires. And they're a pair of operators, a pair of observables, which fulfills the Pauli algebra. And a Hadamard, when you apply a Hadamard to a descriptor, what it will do, it will swap its X component, Qx, with its Z component, Qz, which just gives me QZ, Qx. A C0 is a little bit more convoluted. A C0 acts on 2 qubit, and it scrambles the descriptors component of the 2 qubits together in this fashion. So that's the control qubit. For C is for control, and T is for target. So the descriptor of the control qubit here on the top and the target qubit on the bottom they both get scrambled in this fashion. So the target qubit, X component, goes onto the control qubit. And the Z component of the control qubit goes downwards to sit on the descriptor component of the Z qubit. I know this, I'm not explaining you why, but bear with me, you have to take this rule. So now we have our first step in the computation. We have the second descriptor is meeting a Hadamard, so Q2X comma Q2Z, I apply the Hadamard rule, I permute them. It becomes Q2Z, Q2X. I can push forward my other qubit descriptors because they have not met any gates. Now we meet a C0 gate. So I apply the rule. Q3X is going to go upstairs. So Q3X here moves upstairs with Q2Z. and Q2x is going to go downstairs here with Q3z. Now, a generic unitary operator, which is now what we are about to target here, to tackle, is going to scramble all the descriptor's components, and it's going to have inside its description the parameters alpha and beta. So what I do here is I wrote down as a function dx beta of q1, q1 being the vector encoding q1x and q1z. So it's basically a big scrambling of the descriptor component q1x and q1z, and this function dx also explicitly depends on alpha and beta. But for conciseness, I just wrote down beta. But what you need to bear in mind is this is where alpha and beta sit in the Heisenberg picture description. Correct. That's exactly why I just wrote beta. Okay, so dx of beta is a function that depends on alpha, beta, q1x, q1z. And then we meet a CNOT gate, so we apply the rule. The x component here goes upstairs, and the z component here goes downstairs here, and we're ready to move on. Next step, we meet a Hadamard gate, which permutes the descriptor component here of that system. And then we find a pair of CNOTs with Q4x and with the descriptors of the fourth qubit and the fifth qubit. And when we compute it, I'm just actually caring about what happens here at the moment, but we see that the Z component is going here because it's sort of a CNOT, but it's upside down. If you read it properly, it's gonna take the Z. This is the controlled qubit, so and this is the target qubit, and so the Z component is going here. We're almost done. This gate is just another way of writing down the CNOT, so we can advance here, we can push forward this descriptor, and we are going to write down, this one is going to go downstairs here, and we perform a control Z, which I've not tell you what is done, but you can do it. It's Hadamard, CNOT, Hadamard. Moral of the story, oh, yes, okay. Please realize here that Q2X, Q5Z are going downstairs here to meet with Q2X, Q3Z. So we have Q2X, Q2X. I told you that these operators satisfy the Pauli algebra. So Q2X, Q2X is the identity. So I can discard them. And then once we do the control Z, yeah, it scrambles. It takes this one here, and it actually gonna put it on the X descriptor, on the X component of the third qubit's descriptor. And so my final descriptors looks like this. It does depend on alpha and beta and on the component's descriptor of qubit 1. Now I promised you that the descriptors permit to recover the state vector. And so in particular, I could be interested in computing the reduced density matrix of qubit 3 at time 8. It's expressed by this formula, where the boldface 0 stands for the Heisenberg state. It's a constant 0 state. And note that if I were to, I can also compare it with the descriptor of qubit 1 at time 3. And it happens that the sandwiches are going to yield, the sandwiches being the bracket, the expectation values, are going to yield the same things. Why? Because if we look at the descriptor of qubit 1 at time 3 and the descriptor of qubit 3 at time 8, they're almost the same, but the only things that are different is the Q2Z, Q4Z, Q3Z, Q5Z operators, which, because they fulfill the Pauli algebra, have eigenvalue 1 with respect to the state vector ket 0. And so they are completely oblivious to the state vector. And so the reduced density matrix here, if we perform the computation, it is the same result as if we compute the reduced density matrix of qubit 1 at times 3, which is after Alice has prepared her qubit. And as you may guess, it gives psi. And so all this to say that the state, or the reduced density matrix corresponding to this pair of descriptors at time 8 on qubit 3 is the pure state psi, alpha 0 plus beta 1. So we can recover the Schrödinger story from these calculations. Okay. Now, here, if I put in green where alpha and beta start to appear in my quantum network, I can put the wires in green where everywhere in the network where there's an explicit dependence on alpha and beta for those descriptors. And you realize that the information flow of alpha and beta in the teleportation system is completely local, and it's transmitted by the classical bits. Now I may hear the objection, hang on, but I thought that the transmitted bits are classical. They're supposed to be classical bits. And I'm making this whole model with quantum bits. It's a great question. And indeed, even the discoverers of teleportation, they made us believe that teleportation hinges on purely classical information. But we of course know that there's no such thing as purely classical information, and this resonates well with many conversations that we've had this week. The name of the game is to explain purely classical information in terms of quantum systems, and not vice versa. So purely classical information is instantiated in physical systems, which, whether you like it or not, satisfy quantum theory. And so I'm going to make some remarks to convince you that indeed these two bits are classical. The first one is that we can get an environment that passes by and that decoheres those two qubits in the basis of that has been selected by the measurement process. So they have random descriptor components, QE and QE prime. And when they see not my quantum system, those components are going to go downstairs. QE prime is going to get here, and QE is going to get here, QEX. However, they do not make it all the way to qubit 3. Because this control X and control Z select the Z component of the descriptor and is oblivious to the X component of the descriptor. So the effect of the environment is not destroying the process of teleportation. Hence, we could say that the transfer of Q4 and Q5 is robust to decoherence, which is a property that we'd like of classical information. You can also say, but Charles, you promised us that Alice would use a telephone to communicate the classical bits to Bob. And you're not using a telephone, you're bringing qubit 4 and qubit 5 to Bob's location, which in a sense sort of, if I'm ready to transport qubits from Alice to Bob, I might as well use this channel to teleport the qubit in the first place. However, well, it still shows that it is robust to decoherence, which is already a nice feature. But we can model the telephone. Obviously, when I use a telephone, I'm not sending a precise quantum system from Alice's to Bob. I'm using a chain reaction in a collection of quantum systems. But the classical information can make its way from Alice to Bob. So we could model a chain reaction with systems 4', 5', 4', 5', and what we find if we do this is that the descriptors of the final qubit is going to have the dependency of on Q4'Z, Q4'Z, Q5'Z, and so on. But it does not affect the expectation value, and it yields psi at the end of the protocol. And so, not only that the transfer of Q4 and Q5 is robust to decoherence, but it's also realizable in a chain reaction that resembles a classical communication. Okay. How much time do I have left? About 10 minutes. Huh? Including discussion?
Not including discussion. 15 minutes.
Okay, great. So coming back to the problem of teleportation. How do alpha and beta make their way from Alice to Bob? Now, I'm aware that you sort of had to believe me and jump in my boat in my calculations on how descriptors, components, crumbles, and so on. Please, I hope you did jump in my boat. But if you read the proceedings, then don't jump in the boat and be critical. But for now, at least I hope that I persuaded you of the explanatory power of Heisenberg picture descriptors. How do alpha and beta make their way from Alice to Bob? not through the collapse of the state vector. It remained constant in the Heisenberg picture. Not through non-local influences, allowing them to fly across the entanglement. The transfer has not been mediated by the non-local quantum potential. And the EPR pair is not a channel which proceeds into the past and then into the future again. It is not because of global rather than local properties that have carried the information. This is a very seductive explanation in the Schrödinger picture. In the Schrödinger picture, it seems like alpha and beta are all over the place on the global state vector. But the purely local descriptions make the case that it's clearly not. It's not through the non-locality of Everett's world, but alpha and beta have been transported simply, prosaically, in the qubits Q3 and Q5 as they traveled from Alice to Bob. I think this makes the case that we're still very young in our understanding of classical. We've been fooled by teleportation. We thought that the bits in teleportation were classical. They are quantum. So I will always remember this day where I explained the teleportation protocol to Gilles Brassard, and he, in the Heisenberg picture, and he right away told me that it was the most satisfactory elucidation of teleportation that he's ever heard. So I hope it will have the same effect on you. Of course, I took Gilles on a journey, a like 5-day talk, seminar, whereas I'm just doing 20 minutes, but hopefully you'll be curious about it and you'll learn more about it. And this brings me to some very important questions, which I hope will settle issues. Are we still free to claim that quantum theory is non-local? We are not. Because I've exhibited, or Deutsch and Hayden have exhibited, and I've told you about it, that there exists a mode of description which is complete and local. And we cannot hope for a better criterion of locality. Because once you have, of course, a local description of quantum systems, you're always free to mix it up into an ugly space and say, well, in my mixed up description, it is non-local, so quantum theory is non-local. No, that's a mistake. Quantum theory is local because there exists a local mode of description, period. And so I told you about teleportation, which is one of the fruits or one of the manifest example of the explanatory power of Heisenberg picture descriptors. But I'd like to maybe tell you about some other. In my ABC paper, I make the case for super dense coding. So super dense coding, Alice and Bob share a pair of entangled particles. And with Alice's local operation, she can change the Bell state to 4 possibilities. But it looks again like it hinges on this global property of the Bell state in order to be able to communicate with 1 qubit of communication 2 classical bits. But when you do it in the descriptor framework, you see where the 2 bits sit. They sit in the local descriptor of Alice, and they obviously don't touch the local descriptor of Bob. Since I had the pleasure to speak after Yakir Aharonov, I thought it would be good mentioning that the work of Chiara Marletto and Vlatko Vedral, Aharonov-Bohm phase is locally generated like all other quantum phases. This again needs to jump into the Heisenberg picture of quantum theory to have this explanation. So on that, I'll be happy to have a conversation, and these are the main references. Thank you very much.
Thanks for the talk. I'll start with Lev.
I don't know, maybe I don't have to stand up. Can you go to the slide where you claim that in Schrödinger picture you cannot explain teleportation?
Yeah.
You presented it and then you said that you cannot. I think if I understand correctly the story, your story is about universe. When we talk about teleportation, we talk about our world. And the whole idea of many word interpretation, although Deutsch Haydn kind of trying to say it's many word interpretation, trying to be clearly with us. But no, it's the part of the whole universe. There is this part that many word interpretation, there is no collapse. There is no collapse here, no question. But also, there is no many words. The many words, it's when I perform my measurement, I split the word. So here, now this slide before one, the one which you kind of said that already alpha and beta are there.
Oh yeah, okay, this one.
Yes. Yes. Here, if you look on one line before the last, we have phi plus, phi minus, psi plus, psi minus. And then, according to the procedure, we perform a measurement, which one it is. And after this classical measurement, we have we enter one of the words, we split into 4 words. And in every word, alpha and beta are already in the last one.
I understand, yeah.
So the whole story is sitting, and this is, we can understand teleportation in Schrödinger picture in every word. In every word, it jumps there, and it jumps in the moment of a measurement. So there is no any other explanation within the word, but saying that the non-locality of a word, this is what explains how the information at alpha and beta moves there. And maybe
I understand your point, Lev. I can comment. So I have not commented on the problem of recovering the Schrödinger story that we have when we have 4 terms. Like in teleportation, in the Schrödinger story, we're going to have 4 highly decoherent terms that you call worlds. But Sam is going to speak about how relative state can be defined in the Heisenberg picture. And so there is a sense in which we can rewrite the descriptors of the classical bit as a sum of 4 descriptors, which corresponds to your 4 worlds. But on top of that, this foliation into 4 worlds is completely local because of the locality of the description. So I understand your challenge. You're basically saying, with what I have presented, we don't see, we cannot, it looks like it's a completely different story, and we cannot jump back on what we know. But I claim that we can. And Sam is going to explain how relative states can be defined in the Heisenberg picture formalism.
So let me make a critical comment on your presentation. You made the claim that the bits that are transmitted between Alice and Bob by telephone are really secretly quantum bits, and I must object to that, because I think if you claim that, and I think that the logical consequence of that is that there is no such thing as classical information theory. I think you have to give up on classical information theory as a thing that exists. You say really everything is quantum information theory, because these are just classical bits. You just like we're communicating with a classical channel, those are also classical channels. So how would you respond to that criticism?
Yeah, thanks. Classical information theory is instantiated as a subcase of quantum information theory. And when you have a decoherent state and you look at its reduced density matrix, we can speak of its Shannon information, and it looks like a probability distribution, and we can make sense of classical information in that sense. But my claim, well, I took as a premise that the world is quantum. My telephone is made of quantum systems. And yes, it looks like it's classical to me, but that's, again, the whole program of why we're here today, is try to understand how the quantum theory can help us make sense of classical.
Yeah, well, actually, it's a rather similar question. I mean, look, Charles, lovely framework for thinking about this, but I don't quite get it. The classical channel, it's really just telling Bob what was the outcome of Alice's Bell measurement. It's something you can put into, there's very little information there. Whereas alpha and beta encoding potentially vast amounts of information. So I just don't quite get that. Can you try?
Yes, thanks. Okay, there's one thing I could have mentioned, but for conciseness I did not, is that if we were to intercept these physical systems, Q4 prime, Q5 prime, and we try to read out alpha and beta, we can show that there's nothing that an eavesdropper could do to try and read out alpha and beta from this. So in this sense, alpha and beta is called locally inaccessible information. And it only becomes accessible again in Bob's location once he basically holds the key to unlock this locally inaccessible information in the name in his descriptor components. So, but to come back on your question, you said the telephone is classical information. Wouldn't you grant that any sort of telephone that we can imagine is ultimately made of quantum systems? And the Heisenberg descriptors are a way of describing each quantum system as being a quantum system, fully locally. And so this is the sense in which I was modeling the telephone by a sequence of qubits in this case, but it could obviously be a more elaborated model of quantum systems.
I have a quite general question about the approach. How should I understand entanglement entropy on this picture?
Yeah.
It plays a very fundamental role from everything as kind of pedestrian, no pejorative sense intended by that term in condensed matter physics to the very highfalutin black hole thermodynamics. How should I understand what seems to be the manifest non-locality of quantum mechanics that makes the efficacy of von Neumann entanglement entropy possible?
Yeah, thanks. So you spoke of entanglement entropy, which is the fact that if it's basically a measure of entropy, which is when you look at one subsystem, its reduced density matrix will not be a sharp distribution. And one way to look at it, here we have the descriptor at time 3 of an entangled pair. And you can watch that if you try and compute the associated density matrix here, it will have it will be associated to a mixed state. So you can basically recover the old argument. Or another way to say it that is probably more in hand with the Heisenberg descriptors is that there is no sharp observable for that system that belong to that system alone. So the only way to get a sharp observable would be to multiply some observable of that system with some observable of that system. For example, Q2x and Q2x, Q3z would cancel out the Q2x, and we would have a sharp observable. So there's no sharp observable that locally belong to a single qubit. This is the signature of entanglement in the Heisenberg picture. This temperature? Yeah, if you speak, well, I'm not sure I understand, but if you speak of temperature, then I have in mind some sort of e to the minus beta and a density matrix that corresponds to some Boltzmann distribution, but I don't know if that's what you have. Maybe we take it off the record.
I have two comments of a different character. One is just coming back to this telephone. There's only one information theory. It's Shannon information. Now you can apply it to bits, which by definition have only two possible states. You can apply it to spin half particles that have infinitely many possible states, which are given by your alpha and beta. It doesn't change the information theory at all. In this protocol, all that's required to be sent to implement the protocol are 2 bits, Shannon bits. That's all that's required. You may say, oh, but I have to send a quantum system physically because physics is quantum mechanics. Doesn't matter. If Alice sends a note, classically, of course, it has more than 2 states, right? She could write in cursive, or she could write this way, or she could write. So what? I mean, the point is the protocol merely demands that you resolve between 4 possibilities. That requires 2 bits of information. Period, end of story. The other thing is, the reason they gave that Nobel Prize were tests of violations of Bell's inequality at space-like separation. That's the reason they say it shows non-locality. Quantum teleportation is puzzling, but one thing it sure doesn't do is violate Bell's inequality at space-like separation. So to say, even if it were true, I have a local understanding of this, would not at all have any influence on the reason they say those experiments were so important.
Yeah, thanks for the questions. So I'll start with the second one. It isn't, yeah, it is the reason why the Nobel Prize has been awarded. But people will tend to say that a violation of Bell inequality is equivalent to ruling out local realism. I think that is just not calling, it's not attributing what local realism is. So what a violation of Bell inequality claims does is that it rules out local hidden variable theories. Well, all right. I think I do understand very well the violation of Bell inequalities. So there's no way to pre-implement the distributions inside a classical theory of information to give rise to Bell correlation if we have, okay, well, I'll let you say no, but the claim about local realism is that does there exist a theory of, a way of reading quantum theory in a way that is, as I mentioned, completely local, the information is completely localized in system, and that it reproduces all that we want to observe on quantum theory? And the answer is yes. And so...
No, it's not. It doesn't have Bell's definition. You need to explain Bell's definition of
But Bell's definition of locality demands to state it in terms of classical probability distribution. Thank you.
I want to go back to the Deutsch-Hayden claim about, you know, once I've got a local formulation of the theory, then the theory's local, period.
Yeah.
The worry is that there are relatively clear, cheap ways to make theories local. I'm not claiming this is a cheap way, but there are cheap ways. I can just attach a copy of the state of the universe to every local system. I can say the new state, whatever my wildly non-local description is, I can say, well, on my new theory, the state of a system is the ordered pair of its state on the old theory plus the state of the universe. And then, well, in a sense, it's horrendously expensive. Yes, I mean, call that the monadology move for Leibniz fans. I mean, that framework is formally going to be local, but clearly it's not. I mean, it's not telling us that the theory is interestingly local. So I don't think this move has that character, although there are bits of it that sometimes worry me. But I just want to flag that it seems it's a bit more needs to be done to clarify that a theory is local just because it has a local formalism. We have to be confident we weren't making moves of that kind.
Yeah, thanks. It seems like what you suggest still would not fulfill the Einstein criteria of locality, because you seem to be strapping on each space-time point or in each localized system the description of the whole universe, which then if Bob does something on his system, it will affect this description here. So it does not fulfill the Einstein criterion. And yeah, basically it's a challenge. Try and find other ways of looking at locality. And I think they seem to be, so far there was like 3 different pieces in the literature. And the fact that they were all equivalent was sort of an interesting result in itself. Yes, there is, yeah. Because it sort of, in the background, assumes that Bob is free to sort of do whatever local operation in it. And this operational definition is required to make sense of locality analysis side.
Okay, why don't we thank the session and go for our coffee break.
Thank you.